Hey guys, in today's video we are going to solve one more LeetCode question, that is question number 1436, destination city. In this question we are given an array named paths where path I represents city A and city B, which means that there is a direct path from city A to city B, and we have to return the destination city, that is the city without any path outgoing to another city. This is something that we need to remember because this is the only point on the basis of which we are going to create our solution. And the second point that is given to us is it is guaranteed that the graph of path forms a line without any loop, so there won't be any cycle. Therefore, there will be exactly one destination city. And if we see some of the examples in this, we can see that this is the path array, and it is kind of straightforward, like from London to New York, from New York to Lima, and then Lima to Sao Paulo. And that's how Sao Paulo becomes the destination. So now let's understand how we can form a solution. Before that, let's just see some of the constraints. So in constraints, we are given the length of the paths which would be greater than equivalent to 1 and less than equivalent to 100. And path I will always be equivalent to 2. That means that there will be only two cities, city A and city B, at any index in paths array. And then city A and city B won't be equal ever. So these were some of the constraints. Let's see in how many companies this has been asked. So in last 6 months and from 1 to 2 years, this has been asked in these many companies. So let's now see how we can solve this question with this example. So in this example, we can see that the length of paths array is 3, and the first element is having two cities, city A and city B. Now what is given to us in the question is that destination is the city without any path outgoing to another city. So if I see this whole list, nested list, I can consider that A is a node, and from A there is an outgoing edge to B, right? From A city there is an outgoing edge to B because this is the direct path. Then from B there is a direct edge towards C, and then from C there is a direct edge towards D. So if I see this graph, this whole graph, I can see that D is the only node from which there is no outgoing edges. So this is what that statement means. Like, we need to find a city which doesn't have any outgoing edge or outgoing path. So how we can find that? So let's see the brute force approach. So I will traverse this whole path, and what I will say, like, firstly I will come up to this place and I am saying that my city A at this index is apparently in this example equivalent to A, and city B is equivalent to B for this index of path, right? So now what I will do is I am saying I am having city B equivalent to B at this index. So now check this whole path array again. If any of the city A is equivalent to this city B, and if not, then we know that this city B is the destination, right? So let's check for this one. So now what I will do is I will come up here and I will check the city A, and I'm saying, is this city A is equivalent to my city B? So no. Then I will go to next index. Again I will check city A. City A is equivalent to city B, so yes. So I know that this city B is not the destination. So what I will do is now I will again update these two pointers, that is city A and city B, and then again check for those city A and city B again through this whole path. So what I meant is, now I am at this index and my city A will be equivalent to B and city B will be equivalent to C. And for these 2 pointers now, these 2 pointers, I will again check this whole path. So again I will come up here and see city A. Is this city A is equivalent to my current city B? No. Then I will go to this index. This city A is equivalent to my city B? No. Then again I will go to this index. Is city A is equivalent to my city B? Yes. So now I know that this city B is also not my destination because this is present as city A in some other path, right? So again I will update my city A and city B. So now my pointer is updated and I will be at this position where my city A will become C and my city B will become D. So at this place, again I have updated my 2 pointers and again I will repeat the procedure where I will check city A of every index and compare it with my city B. So is this same? No. So I will again go to this place. Is this same? No. Then I will again update and check for this city A. Is this same? No. Now I know I am out of bound and I have ended the list. I have ended the traversal. So now at the end I know this city B was not present as city A in any other path. So now what I can say is this is the destination. So this was a kind of brute force approach where I was firstly standing up at one place and then checking for all the possibilities in rest of the array. Not only rest of the array, I was again traversing the whole array again. So the time complexity of this brute force approach will be around big O of n square, where n is the length of path, right? So this will be the time complexity. And we know that this is not efficient. This is quite expensive. So can we optimize it further? So let's see how we can optimize it because we can. So how we can optimize this whole approach. So first thing is clear to us that we need to check all the city B's because city B's are the one which holds the potential to be a destination because we are going from A to B, right? So all the B's or all the city B's or all the second elements in these nested list are the ones which holds the possibility of becoming a destination. And what was the condition on the basis of which we were deciding is that they are not appearing as a first element in any of the paths. So rather than using a nested loop and checking for this destination in rest of the paths, what we can do is we can create a set and we can store all the city A's inside it. So like this A, B and C. So this set will consist of A, B and C, all the city A's, right? Or all the first element. And after this, I will traverse through this path again. And what I am saying is simply check the second elements, the elements which holds the potential of being a destination. So I will come up to this place. I will check if B is present in my city A set, then I know this is not a destination. Then I will go to next index. I will again take city B and I'm saying check if C is present in my set or not. It is. So I know that C is also not a destination. Then I will come up to this place. I will check city B, which is D, and is this present in my hash in my set? Then no. Then I know that this is the destination. So this is how we can optimize the approach, where we will traverse through this path once and create a set of all the city A's. So this will hold all the city A's or the first elements of any path, and then what we will do, we will again traverse through this path and check all the city B's, and if they are present in this set, then they are not the destination, but if not, then definitely it's our destination and we will return it. So this is how we optimized it. So in this approach, what will be the time complexity? Time complexity will be big O of n for creating this set plus big O of n for checking if the second element of any of the path is present in this set or not. And as we are looping through second time, we are checking in a set, so the lookup time is around big O of 1, so we don't have to consider that as a constant time. And when we will solve this thing, it will become 2 big O of n, so 2 is constant, we can ignore it. So overall time complexity is big O of n for this approach, and space complexity will be also equivalent to big O of n because we are creating a set in which we are restoring all the city A's. So this was the optimized approach, and I think this is pretty clear. So now let's jump to the coding part, where we will be coding this solution in 2 programming languages, first Python and then Ruby. So let's just code the Python solution. So firstly, let's define our hash set. So in Python, this is how we create set. After this, what we are doing is, for I in paths, hash set dot add I 0. After this, again we are doing same thing. So again we will run a loop for I in paths, or we can name it as path, so it will make more sense, for path in paths. So inside this, what we can do is we can say path 1. If this is not in hash set, then return path 1, and at the end, if we step out of this loop, then add simple return statement. So let's submit it and check. So this has been accepted. Now let's quickly code Ruby solution. So in this as well, let's create our hash set. So in Ruby, we create set in this format. After this, what we can do is paths dot each do path, and inside this loop we have to populate our hash set. So hash set dot add path 0, then again paths dot each do path, and inside this we are saying return path 1 unless hash set dot include path 1, and that's it. Let's submit it and check. So this is also accepted. This problem was quite straightforward, especially with the help of these 2 points. It was easy to come up with the brute force as well as an optimized solution. So I hope this video was helpful for you all, and if it really was, then you can like this video, subscribe my channel, and I will soon come up with more such questions. And till then, take care and keep messing with algorithms, and thanks.